So now that we spent a little bit of time studying continuity, we're going to dive into a couple of ideas that allow us to apply this idea of continuity in pretty powerful ways. One of those ways is called the intermediate value theorem. And if you look a little bit down on your page, we have the intermediate value theorem expressed in mathematical notation. And if you look on the second page, we have a delta math example that looks kind of scary. Sort of like our idea of continuity, this is actually a really simple idea, the intermediate value theorem, that looks more challenging than it needs to when you put it into this kind of precise mathematical notation. So we're going to start with a couple of examples of just traveling around the city. We're going to imagine we're an Uber driver, and we're just going to consider a couple of scenarios. So in the first scenario, we're asked if our odometer, that's what measures how far you've driven, reads 0 miles when you start your shift, and you pick up a group of tourists and you drive 18 miles to the MSI. And the question is, I'm going to underline this word must, because that's going to be important later. Must there have been a time when the odometer read 12 miles? And the answer here obviously is yes, right? So if you drive 18 miles and you started at 0 miles, you have to cross 12, right? I'm going to write this in a particular way though. So notice I use this word continuously in my explanation, right? And this is important because that's the assumption here. So if my odometer was not a continuous function, this wouldn't be good evidence to say it passed 12, because if it's something that kind of jumps around, we don't know where it's going to go. But if it's something that increases smoothly, we know to go from 0 to 18, it must pass 12. Okay. Question B highlights another idea related to this intermediate value theorem. So now we're driving from Chicago to Northwestern, so one end of the city to the other. And if we're driving 19 miles, the question is it possible that you are at some point 22 miles away from Northwestern? And the answer here is yes. So we know in the city, sometimes we drive a little bit out of our way to take a faster route. So maybe I drove a little bit out of my way to get to the Dan Ryan instead of taking Lakeshore Drive. And then question 2 here is must. So I'm going to underline must, underline impossible. So here, must there have been a time when you're 22 miles away from Northwestern? The answer here is no. We could have just gone straight there. So we could have started at 22 and take down to 0, right? I'm going to draw these two scenarios. So let's say here's my distance, here's my time. So here's 22 miles, here's 19 miles. So this is one possible scenario. Or we could have just gone straight here from 19 to 0. So notice every value between 0 and 19, that would be a must, right? But any value outside of that range, that would be like a maybe, right? Could have hit 22, but maybe not. We don't have clear evidence to suggest that we did. Now, here, question C, I think this is the most interesting question. Again, it's an obvious question. If we had 2 passengers and then we had 4 passengers, must there have been a trip where you had 3 passengers? And the answer here obviously is no. And what we can say here, right, is the number of passengers is not necessarily continuous. So if I graphed the number of passengers, it could be, a bunch of disconnected dots. It doesn't necessarily have to be a nice smooth curve. So there's no reason that I would have to have 3 just because it's between 2 and 4. So that's the intermediate value theorem in a nutshell. So these are 3 examples that are going to be important to keep in mind as we study this in a more rigorous way. So basically what we're saying is, if a function is continuous on a given range, so some piece of the function, if we know 2 y values are on a range, we also know that we must touch all the y values in between. We may go outside of that range, but we must at least touch all the ones in between. So that's our odometer example, right? So we have to go from 0 to 18, touching all the values in between. We may, in some cases, go outside of the range. So maybe we hit 22 miles, maybe we don't in this example. And all of this only applies if our function is continuous. Otherwise, we can only guess. So this is not a hard idea. This is common sense, actually. But the notation we use to describe this idea is a little bit tricky. So it says if a function is continuous over the interval a to b, let's draw a picture. So a to b Well, that sounds like x values to me, doesn't it? So a to b, here I'm going to draw. And m is some number between f of a and f of b. This is where it starts to get confusing. Those are clearly y values if it's f of a, f of b, right? So here's f of a. We'll draw it up here. We'll give a y value right there. And let's make a decreasing function. F of b will be down here. So there's our point b. And m is some number in between f of a and f of b. So that's here is m. Then there exists a number c between a and b such that f of c equals m. So what that's saying is c is right here. F of c equals m. So f of c is here. So all it's saying is exactly what we just talked about, that we know if we go from a to b on a continuous function, we have to touch this point f of c. Now we're going to consider some examples. Make sure you read this one. So we're given a continuous function. It really looks like the formulation of our theorem, right? And we have 2 points, right? So we're going to draw a picture. We have -3 and 10 going to be here. I'm not going to worry about the x-axis here. And 7 and -2 is going to be down here. And we note that it's continuous, so we know it's got to be something like that. It could go up and down. It could be forever decreasing. Is there guaranteed a value a in the domain such that h of a equals 1? Well, based on my picture, like obviously yes, right? That point would be here, right? That's all this thing is saying. So here's a, here's 1, right? Our answer, we're going to justify it in a particular way based on how you're expected to justify on the AP exam. So we're going to say yes, and we have to state that the theorem applies. That's what they're looking for in your justification. So we want to say first h of x is continuous, and we're going to restate the points in the question, sort of like you do in like English or social studies, right? We restate some info from the question. And we can say, since our point 1 is between 10 and -2, those y values, there must exist an a that meets our criteria by the intermediate value theorem. Now here, notice -3 is not between -2 and -10. So -3 is down here. So my answer here is no, since it's not in our range. So that's our 22 miles example. Again, this is common sense, right? Except for the notation looks challenging, but the ideas are not hard. So the last thing I want to consider is a delta math example. And the first thing I want to note with this example is you are never going to pick these options. I don't even know why they include them. We're never going to say not continuous or does not exist, because this theorem that we're using proves that things do exist, but doesn't necessarily prove that they don't exist. So like that example of the number of passengers, you could have taken 3 passengers. You could not have. We just don't have any evidence to prove it one way or another. So what you're going to pick is these ones that are a little bit more circumspect if the theorem does not apply. So as you read these, the first thing you want to make sure it says is the function is continuous, because otherwise we can't do anything. And we're going to have to say not necessarily continuous, and the IVT does not apply. And then we're going to say the function is continuous. We can apply the theorem. And then here's where it feels like a little bit confusing, and states that for any value k in the interval blank to blank, there exists a value c where blank blank such that f of c equals k. So the thing to note, right, that is tricky is that c is an x value, k is a y value. So what has to go here is my 2 y values from the text, right? So we have -3 and -5. And then it says, must there exist a value c in the interval? It'll fill this in for you, -3 to -5, where f of c equals -6. And the answer here is no, right? And the logic here is like, since -6 is not between -3 and -5. So we say there may exist here. We don't pick there does not exist, because it might exist, we just cannot prove it. So the thing to know here is where the y values and where the x values go in your proof.